All right, so welcome back. Trying out some different pens today. They should be, I don't know, I think it's going to be increased visibility. So we'll see how that goes. But let me know if the writing gets sloppy because it's this thicker tip. So just let me know if you need some help understanding what's up there. All right, anyway. So last time we were talking about a very conceptual picture of quantum mechanics, and we were describing the atom. So we're describing the electrons around the atom specifically. And so when we talk about quantum mechanics or quantized or quantum this or quantum that, all it means is countable. That's all quantum means. 1, 2, 3, 4, 5, discrete values. How many people are in this classroom? I don't know. Let's go with 50. Maybe 51, maybe 49, maybe 52, but not 53.765. There's a certain number of people, there are a certain number of people in this room. It's countable. That is a quantized value. How high is my hand? Well, you could add some more decimal places to that. You could argue that you could keep measuring that more and more precisely, and that it's a perfect continuum. Or if you have a ruler, then you can only really measure 1 inch, 2 inch, 3 inch, 4 inch, 5 inch. And so whether or not it's quantized or appears to be quantized often depends on your ability to measure and the length scale you're looking at. The weird thing about small things is that they appear to be quantized, meaning that electrons can only occupy certain energy levels around a nucleus. And that's really weird. So a nucleus is a positive charge or some positive charge. Electrons are negative charge. First off, it should be weird, or at least it's weird to me, that they don't just run into each other, right? The electrons don't just swarm the nucleus that they are so attracted to. The second thing we observe that's weird about these atoms is that the electrons, not only do they not fall into the nucleus, but they exist in discrete places around the nucleus and not in between. They don't exist in that region in between. We say their probability density, the probability of finding an electron in those nodal regions, is 0. And so these quantum numbers are a way of identifying all those weird features of electrons. That's what we're doing. We're learning how to identify those different features. What are they called? So what's the symbolism we use? What are they called? What values can they have? Just because something's quantized doesn't mean it just goes 1, 2, 3, 4. It may go 0, 1, 2, 3. It may have negative values allowed. And then we're going to see the spin quantum number, which has values of 1/2, which breaks all that. But we'll get to that. So that's what we're doing with quantum numbers. Quantum numbers are a little bit arcane because they're not something that you're going to walk to the grocery store and use quantum numbers. It's just not going to happen. But if you start getting into electronic structure of atoms, which you will, when you take organic chemistry, we'll use N and L frequently in organic chemistry. We'll use N, L, and M sub L frequently. And we'll even use M sub S occasionally. We don't really usually care about which one we have as far as M sub L and M sub S. We just keep track of whether or not they're different, whether they're the same or different. And so we'll get into that. So that all having been said, this is a table you'd want to be able to generate from memory. You want to be able to generate this table from memory for the 4 quantum numbers. The 4 quantum numbers, their symbols are N, L, M sub L, and M sub S. Those are the 4 symbols for the quantum numbers. For N, we call this the shell. What does it mean? What is N? It's we call it the principal quantum number. What does it mean? It's the shell. It's how far away from the nucleus are the electrons. That's all it is. It's the average distance. Remember, we're picturing atoms, electrons as orbiting the nucleus, or as existing in these probability density orbitals. The orbiting is a particle picture of the electron. Remember, wave particle duality. So the orbitals, something orbiting something going round and round, that's picturing the electrons as a particle. That's orbits. Orbitals are this idea that electrons they don't exist at any one point in time. Rather, they are a probability density where you are more likely or less likely to find the electron at given points. But until you measure, you never really know where the electron is. It's just smeared out over that entire region of space. That's how we picture it. And another picture is just to picture it as a wave function. So these are three different ways. One is pure particle, that is orbits. One is pure waves, that's just wave mechanics. And then there's the wave function, which brings into this idea of probability density. We can do wave mechanics on something that is a particle if we picture it as a probability density. So anyway, that's these two ideas as I see them and how you can think about them. Okay, so that's n. N is the principal quantum number. It's the first quantum number, and it's the number on the left side of the periodic table. That's what n is. So for H, n is 1. All the orbitals in H have an n equal to 1. For lithium and the second period, n is going to have values of 1 or 2. So you can have things in the first shell or the second shell. For sodium or anything else in the third period, n can be equal to 1, 2, or 3. It's a bigger atom. It can accommodate more electrons. It has more positive charge in its nucleus. It needs more electrons to balance it out. Those electrons keep taking up more and more space. That's what n is. It's the shell. How far away from the nucleus are you on average? So n is just the left side of the periodic table. If you're trying to figure out, or at least the maximum value of n is defined by the left side of the periodic table. Okay, so n is pretty easy. L is the angular momentum quantum number. So this is the principal quantum number. I'm not going to write quantum number every time, so we'll call that the principal quantum number, the angular momentum quantum number, and so on. So L, lowercase l, is the angular momentum quantum. And this is the subshell. So if the shell, the principal quantum number, is distance from the nucleus, the subshell is the shape of the orbital. We're defining where is the electron. Electrons exist in orbitals. So what does the orbital look like? Well, it has a certain distance from the nucleus. It has a certain shape. If we're talking about a 1s orbital, it's a perfect sphere. It's nice and boring. If we're talking about anything else, it's going to be a little different. So all of the s orbitals. So let me go ahead and add this into your table. No, that's not what I wanted to add a place, but that works too. That's not what I wanted to do. This is what I wanted to do. How do I want to write that? So we'll do it this way. Greater than or equal to L greater than or equal to n minus 1. There we go. Okay. And so in reality, you're going to deal with 0, 1, 2, or 3 if you have a large enough atom. Bless you. And we call these S, P, D, and F orbitals. So you've probably heard of S orbitals. I've said it a lot. P orbitals, D orbitals, and occasionally F orbitals. That is another way of expressing angular momentum quantum number. So the L quantum number, the number is going to be 0, 1, 2, or 3, up to your shell number minus 1. So the first shell, the first period, those atoms can only have s orbitals. N minus 1 is our max. If our period is 1, if our n is 1, then L can only be 0. If n is 2, so like lithium or beryllium or carbon or any of those, if n is equal to 2, then L can be equal to 0 or 1. It can go up to n minus 1. So it can be equal to 0 or 1. That means L could be 0 or 1. We can have S or P orbitals for the second period. And that works all the way down. So once you get to the fourth period, you can have F orbitals. And then anything below that will have access to all four types, S, P, D, and F. Really see G orbitals. So there's S, P, D, and F. Or anything after F is what I'm trying to say. We don't really see orbitals after F. A professor at University of Arizona, where I went to grad school, his son did calculations to map out what he called G orbitals, which I'm guessing is what we would use as the letter after F if we needed to. And so, his son became a chemist, and he mapped out G orbitals and showed their shape as best he could in 3 dimensions. And you can mathematically keep adding more and more and more orbitals around an atom. It's just not what we observe it. We don't see that happening. So, yep.
So, for N, you said it's the number on the top, or is it the number on the side?
On the side, the left. Yep. So as we go down the periodic table, we are increasing the number of shells of electrons around the atoms. And so what ends up happening is all the atoms in the second period, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon, all of those have electrons in 2 shells when they're neutral. As soon as you get past neon, we're jumping out to a 3rd shell. So the electrons are going to be further away from the nucleus. So when we start talking about atomic radii in this chapter, that's related to atomic radius. How far away are the electrons? Yep. Yep. So N and L are your principal quantum number and your angular momentum quantum number. That defines how far away from the nucleus it is and what its shape is. So here is, if we look at this picture of an atom, a nucleus is positively charged. The first shell of electrons is going to be n equals 1. That can only accommodate s orbitals. L must be equal to 0. The second shell, n equals 2, that can accommodate s and p orbitals. The third shell, n equals 3, can accommodate s, p, and d orbitals, and so on. What those orbitals look like: s orbitals. So this is your Cartesian coordinates, x, y, and z. I know it's a little blurry. You have a sphere that's centered on the nucleus. For p orbitals, just remember L defines their shape. P orbitals, this would be L equals 1. We end up with these 2 lobes. I think of it like a figure 8, where everything crosses this, the origin at 0. So the probability of finding any electrons there, what we're seeing here is probability densities. I guess I should say that. These 2 lobes, all these, the sphere, these 2 lobes, every drawing of orbitals represents the probability density map for finding probability density for an electron in that orbital. What that means is where it's bigger, you're more likely to find an electron. Where it's smaller, or where it's more strongly colored, you're more likely to find an electron. Where it's less strongly colored, you're less likely to find an electron. Although I guess that's not really true for this one. Let me just say the important bits here. The shape, it's 2 lobes. It's 2 lobes. There's a node between them. There's a region of space between the 2 where there is no electron density. So we're going to be interested in counting up the number of nodes. If you look, there are 3 different ways to make orbitals with 2 lobes. And you can call them px if it's on the x-axis, Py if it's on the y-axis, and Pz if it's on the z-axis. So that direction, so shape, p orbital versus s orbital shape, that's L. That's your angular momentum quantum number. M sub L is what direction is the orbital facing? The x direction, the y direction, or the z direction? Now, those are arbitrary directions. There's no x direction on an atom. They're arbitrary. You just assign them to an atom and say, okay, we're going to call this one x, and then everything else falls into place. This one must be y, that one must be z. And so oftentimes we don't really care which one of those we have. We just want to know, are they in the same orbital, px, or different orbitals, px, py, pz. And so oftentimes you'll hear people talk about 2s orbitals or 3p orbitals or whatever. You'll rarely hear about px, py. That's less common, less useful. Yeah.
Think of it as like a cloud instead of being able to like pinpoint where it is. If we're constantly just trying to find a probability of where it could be.
That's the cloud. Yep. Probability cloud, electron density cloud is definitely a word that's used. Electron cloud is a way to think about it. Absolutely. Okay. And so where do these orbitals come from? These orbitals come from trying to fit electrons around a nucleus without ever having them run into each other. So if we want to put orbitals into this around the nucleus, and we try doing that, well, the first thing that's easiest to do that ends up being the most energetically favorable is to put them in a sphere around the nucleus. Great. Now we have extra electrons that we can't fit into the sphere because they repel each other. Where do we put them next? Well, we put them further away from the nucleus into a sphere. That's going from shell 1 to shell 2. Now we're at the 2s orbital, so a bigger sphere. Okay, fine. We have them in a bigger sphere. We want to add some more electrons. You could imagine going out to an even bigger sphere, but it turns out there's an energetically more favorable place between the second sphere and the third sphere. Those are the p orbitals. Instead of adding another sphere, you start having them take these weird angular momentums, adopt these weird paths. That's what angular momentum is. Momentum is how fast you're moving in a line. Angular momentum is how fast you're moving, and it's along a curve. And so if you give them these angular momentums, it turns out they can be about the same distance as a 2s orbital. So you end up with 2p and 2s orbitals at about the same distance from the nucleus. That's the second shell. And then you do the same thing for the third shell, but then you can introduce other weird shapes on top of spheres and figure eights, as I call them. And you end up with something having 4 lobes. So dx, I'll let you read the names for them. So you have dxy, dyz, dz squared is the weird one. So you have this weird figure 8 where both lobes are the same phase surrounded by a donut, none of which actually have probability density at the nucleus. Anyway, I'll let you read about those because being able to draw a dz squared orbital is not in your future. You don't have to worry about that unless you go into inorganic chemistry. And if you do that, then I blame you. So, yeah. But anyway, no, inorganic chemistry is actually really powerful and fun, and you get lots of colors, but I'm not able to do that. So there's a fun battle between them. That's all. Okay. Anyway, so we've covered the first 2 quantum numbers, more or less. The shell n principal quantum number, that's how far you are from the nucleus. L, the subshell or the shape, that is the shape, the angular momentum of the orbital. And then the next one is going to be the we just did subshell. Next one is going to be M sub L. So this is our magnetic quantum number. Which I just said is the direction or orientation. So this is, bless you. So this can have values that range from negative L to 0, or well, M sub L is going to be greater than or equal to L, negative L, and then less than or equal to positive L. So if n is equal to 1, L can only be equal to 0, and m sub L must be 0. If n is equal to 2, L can be 1 or 0. And if L is 1, then m sub L could be 1, 0, or minus 1. Meaning that if L is 1, if we're talking about p orbitals, we have 1, 0, minus 1, 3 different ways to have those oriented in space. That's your px, your py, and your pz. If you do the same thing for d orbitals, which would have to be in the third shell or higher, d orbitals have an angular momentum quantum number of 2. So if n is 3, L is n up to n minus 1, which is 2. And that means they could be 2, 1, 0, negative 1, 2. There are 5 different ways to have the magnetic quantum number for d orbitals, which is what we observe. And that's how you grow that out. And finally, there's the spin quantum number. Spin. And that's always either equal to minus 1/2 or plus 1/2. Those are the only 2 values it can have. Doesn't matter what n value you're talking about. Doesn't matter what L or m sub L you're talking about. So this is phrased a few different ways. One is the direction of the spin of the electron. So I'm putting that in quotes. Direction of spin in electron. And so this name, you can picture it. This is not how we understand them to actually exist, but you can get a lot of correct outcomes from this model. So here's a model that will get you a lot of right answers, but isn't like a real physical picture. So picture electrons as sort of spinning like a top. And so they can be spinning in this direction, or they can be spinning in this direction. They have an axis that's defined by what orbital they're in, and they can either be spinning up or down. That's that spin up or down that you see, those arrows pointing up or down when we pair orbitals, or we pair electrons in orbitals. So you might have seen this before, where you put electrons into an orbital where one is up and the other is down. If you haven't seen that yet, we'll see it. You've seen it in the text and we'll see it today. But spin is a quantum property, as far as I know, and as far as I have heard and been taught. It's not spinning. Right? It's just a weird property of quantum particles that we call spin. And physicists in more recent years have gotten quirkier with their names, like quarks, and they have up quarks, down quarks, top quarks, bottom quarks. They just start playing with names, because there's no macroscopic physical equivalent that we can say, oh, this acts like this. It acts like a quantum mechanical particle with its own properties. So anyway, that's as far as I'm going in that weird world. It's fun to learn about, a lot of fun to learn about. If you do the math, this starts to make sense. If you go and take the calculus and go do the quantum mechanics, if you go play with it, it starts to make sense in a weird way. That's the best I can offer you. If you are interested in that, or if that sounds weird, I encourage you to read a book about quantum mechanics, like not necessarily a textbook, just like a pop culture book about it, and about the history. And they're always, it's a really interesting evolution. If you follow how quantum mechanics were developed in real time alongside other historical events, including art and music, you'll see that things developed in a very similar way across a bunch of different fields. So there was sort of this explosion of these ideas that are associated with quantum mechanics that were sort of more abstract and, spacey. But it works. It works. We wouldn't have any of the technology, or a lot of the technology we have today, without understanding quantum mechanics. So that's my sales pitch for you to go a little bit further with that if you're interested, but it's not necessary for this course. Okay, so these are our 4 quantum numbers. that is what we want to be able to do. Let's go ahead and run back through this using the slides, and then we will get into the rest of chapter 6 today. Unless there are questions about this or about the homework or anything. So our quantum numbers, again, we want to be able to generate that table from scratch. So you'd want to be able to generate this from memory. And so whenever we talk about the principal quantum number n, it can have values of 1, 2, 3, and 4. That's our energy levels, or how far up or down the energy axis we are. This slide's a little jumbled. So you can think of that if you're thinking of the orbit picture, how far away from the nucleus are you in terms of the orbit? Orbitals is sort of a more complicated picture of an orbit. It's just all the different ways to put electrons in that region of space mathematically without them running into each other. So you can play with the math, and I say mathematically, let me just say one more thing about that. If you solve the wave function for electrons and you start piecing them in around the nucleus, okay, I'm going to put one in a sphere here, one in a larger sphere, or I'm going to put them in another larger sphere, and so on. You could do that. You could do the math on it and figure out what the energy would be to put electrons in those orbitals. And that's a reasonable thing to do. But if you play with the numbers, you'll find there are other shapes that you can imagine the electrons taking, these orbitals, that allow them to become closer to the nucleus. And by bringing the negative charge and the positive charge closer together, you're bringing the system down in energy. And that's what nature does. It just goes down in energy. Water flows downhill. And so the electrons don't occupy sphere and sphere and sphere and sphere. They have these other weird shapes. And if you keep playing with the numbers and getting the smallest value you can for the energy of those electrons around a sphere, you end up with these orbitals, these shapes. That's where that comes from. So nature finds its way down to the lowest energy states. All we're doing is modeling that mathematically and showing it as three-dimensional pictures. So anyway, that's why. Move on. So we talked about N, principal quantum number. L, angular momentum quantum number. That's the shape of the orbital. S, P, D, or F orbitals. We call the S orbitals L equals 0, L equals 1, we call P, L equals 2, we call D, L equals 3, we call F. About this idea of radial nodes. So if the electrons aren't going to run into each other, they're going to have regions of 0 electron density in order to occupy the same part of space. They're going to have to be able to sort of go around each other, is a way that I think about that. Again, that's a very particle picture, not a wave picture, but it'll get you the right answer. They are defined by L. They are, so if, it's right here. So the number of radial nodes is always going to be equal to 1 n minus L minus 1. There we go. N minus L minus 1. Because that doesn't help me. What I think about is S orbitals. You can do it with that. If you know what your N is, say your N is 1, then L must be 0. If you take 1 away from that, there are 0 nodes. So the 1s orbital has no nodes. It is completely filling in the space around the nucleus. As soon as you get away from that, you start introducing some nodes. As soon as you get away from the 1s orbital, you introduce more and more and more nodes. It's not only how far away you are from the nucleus, which is why n is in that equation, but it's also the shape. If it's a 2s orbital, that has fewer nodes than a 2p orbital. The 2p orbital has that figure 8 shape. We saw that node in the middle there. So anyway, that's how we calculate. If you wanted to calculate the number of nodes or keep track of the number of nodes, you could also just look at the shapes and figure it out from that. So here is a 1s orbital. The probability density goes up. And as far as distance from the nucleus, it goes up, it comes down, and that's it. For a 2s orbital, you have a probability density, and then a second probability density. And the space in between them, there is no probability, that white space. Whenever you see the two colors here for orbitals, that represents phase. We haven't talked much about phase, but remember, these are waves. Waves have amplitude. Whether that amplitude is above or below that x-axis, we call that the phase. And so, well, that's one way to think of phase. Another way to think of phase is whether two waves are traveling next to each other and they're both up in time and down at the same time. That's in phase. Remember this idea of constructive and destructive interference? If two waves are in phase, they will be complementary. If two waves are out of phase, one is going up while the other is going down, they will always cancel each other exactly. And so that's this right here. That's two phases canceling each other. There's a blue phase and a red phase. Wherever they would meet, there is a node. You'll see that as you do more orbital pictures of atoms. You'll see these phases come up again and again. We don't need it right now. All you need to know is that these nodes exist. That's it. They exist. And isn't that weird? You know, isn't that weird that there are these regions of space where there are no electrons? Okay. Yeah, so the P subshell has a dumbbell shape. D and F are more complex. Three-dimensional regions where the electron is likely to be found. And we'll move a little faster. Magnetic quantum number, that specifies the orientation of the orbital in space. And if we wanted to figure out what values are allowed, we know that we can go down to negative L through 0 up to positive L. And then finally, generacy, right? We need to talk about this. When referring to an orbital, we usually need the N and the L. So I was talking about that earlier, a 2s orbital or a 3p orbital or a 3d orbital. In the case of the hydrogen atom, all the orbitals within N are the same. They're all that 1s orbital. And so whenever orbitals are the same energy level, we say they're degenerate. So degenerate is often used as a derogatory term, you know, a degenerate, but but here it just means same energy. And so in chemistry, degenerate orbitals or degeneracy refers to electrons having the same energy. So if we think about atoms more complex than hydrogen, they have more than just 1s orbitals. And so it turns out that if you go out to the second shell, where we have 2s orbitals and 2p orbitals, we have a big sphere that has a node, and we have these dumbbell-shaped things. If you go out to the second shell, the s and p orbitals are not exactly the same energy. They're close. So we consider them all to be in the second shell, but they're not exactly the same. And so what that ends up meaning is that the s orbitals in the second shell are degenerate, and the p orbitals in the second shell are degenerate, but they're not degenerate with each other. That means that they'll have different interactions with other electrons, other matter, so we can treat them differently chemically. We can also plot the relative energies, and this is what you'd want to be able to do. You want to be able to generate this plot from scratch. Blank sheet of paper, make this plot. What you'll notice is that as you go from the 1s to 2s to the 3s, we're going to stop there. The 1s to the 2s to the 3s, forget about the 4s for a minute. So you go from the 1s to the 2s to the 3s, there's a big jump in energy. Energy's on the y-axis. The horizontal lines represent orbitals. That is the energy of a 1s orbital. So energy's on the y-axis. All we're saying is a 1s orbital is here. If a 1s orbital is here, then roughly to scale, a 2s orbital is here. If that's our scale of the energy axis, that big gap is the gap between 1s and 2s energetically. 2p is only a little bit higher. So we consider these to be in the same shell, the same distance from the nucleus, on average, roughly. The distance between the 2s and 2p and the next shell, the 3s, is bigger than the distance between the two subshells. but it's not as big as this difference. So as you go further and further away from the nucleus, the difference in energy between the shells decreases. They start becoming more and more similar because you're getting further and further away from the positive charge that holds everything together. The nucleus. So, but as we get up here, we see the three s orbitals, the spherical-like orbitals, sphere-like orbitals, are lower in energy by a little bit than 3p orbitals. The 3p orbitals have those lows, those figure eights. Then we get into, and the 3ds, which are a different subshell and still part of the third shell, those are also higher in energy than the p's or the s's. D within a shell, D will always be higher than P, will always be higher than S in energy within a shell. There's this weird crossing point for the 4s orbitals. It just so happens that because the distance between the subshells is increasing pretty fast, and the distance between the shells is decreasing pretty fast, they end up having this crossing point where the 4s orbitals are a little bit lower in energy than the 3d. We'll need to remember that. When we're assigning electronic structure to atoms, that's the weird spot. And so long as you identify that, everything's fine. It all makes sense. Go 1s, 2s, 2p, 3s, 3p, and then slow down. After 3p, slow down and think a little bit, okay, wait, this is where I need to make a change. I need to consider the 3d versus 4s. Fact. So each of these energy levels represents orbital. This would be my 1s orbital. N is equal to 1. This is my, and N is equal to 1, L is equal to 0. This is my 2s orbital. N is equal to 2, L is equal to 0. These are my 2p orbitals. N is equal to 2, L is equal to 1. Now there are 3 of them, they're degenerate. So I must have another way to differentiate them besides just N and L. That's where we use M sub L. So -1, 0, or +1. Or we could say PX, PY, PZ. So as soon as you start seeing those subletters, the subshells, that's telling you have degenerate orbitals. And then spin. The rule is you can only have 2 electrons per orbital. And the other rule is no 2 electrons can have the exact same 4 quantum numbers. So they have to have some difference. So if I have an electron in the 1s orbital, it's N is equal to 1, L is equal to 0, M sub L is equal to 0. And then the only thing left is spin. If I put 2 electrons in this orbital, they have to have different spins. They must. Otherwise, I've defined the same electron. If you have the same 4 quantum numbers, that's the same electron. It's like a social security number or an address. There's one set of quantum numbers for one electron in the world. Every electron you point to has a set of quantum numbers. And not the same for any other atoms. I have to be careful here now. Same for any other electrons in that particular atom, I guess I should say. Particular atom. Yeah. So, all right. And that goes to the Pauli exclusion principle. You probably read about that or heard about that. And it just says you can't have 2 things at the same place at the same time. And you know that. If you ever driven in Bowling Green, you've probably been rear-ended. I know I have. And so people learn that the hard way. So anyway, all right. And so this is this idea of spin. And we actually use magnetic fields to align these spins in a magnetic field. That allows us to get structural information about molecules. So, how do we know what these molecules look like? How do we go into a lab and figure that out? Right down the hall here, there's an instrument, costs about $400,000. We fill it with liquid nitrogen every week. We fill it with liquid helium, which is getting more and more expensive because it's a finite resource on Earth. Stop filling with it. Anyway, we fill it with liquid helium because it's especially cold, which is what we need for the magnet, every few months. And that goes down, liquid helium is around 2 Kelvin or 4 Kelvin. It's pretty darn cold. That helps keep the magnet very cold, which allows us to have a very stable magnetic field. which allows us to align nuclei, which allows us to get information about chemical structure. Now, that all sounds really complicated, but this technology is so developed and has been associated with so many Nobel Prizes, and MRI technology is the same technology. It's so developed now that I have high school students using that. I've had high school students using it. You put a sample into a solvent, you mix it up, you put it into a spectrometer, hit some buttons, and then you get out some spectrum, and then you learn how to interpret the spectrum. And so anyway, it's an incredibly useful tool, magnetic spin. So even though it's this weird property, it's useful. If you ever have an MRI, that's what they're doing. They give you an MRI contrast agent. They're fixing that spin. They're trying to help those spins last so that they can see them, because they want those spins to align with the magnetic field, or they want them to relax quickly, one of the two. Anyway. So yeah, the Pauli exclusion principle, no two electrons in the same atom can have exactly the same set of quantum numbers. Otherwise, they'd be the same electron in the atom. So the spin quantum numbers are always either +1/2 or -1/2. And if you have two electrons in the same orbital, they must have opposite spins. That's it for the quantum numbers piece of this. Make sure you can generate this table from scratch, and you'll be all set. Work problems, best bet. The exam from 2023 is on Blackboard, and you can look at that in the key. That's a good resource in addition to the book. But I'd start with the book. Yeah.
If you go back to figure 6.23, what does that B stand for?
Oh, that's magnetic field. Yeah, B0 is magnetic field direction. Yeah, thanks for asking that. So magnetic fields like have a north and a south pole, and if you align so whenever we think, okay, so the word is one way you can think of spin. Who here is taking or has taken bless you, physics with electricity and magnetism? Just one or two? Okay. So what you'll learn is that if you spin, if you have electrons, or if you have a magnet and you spin it around a wire, you get electrical current. That's those turbines we were talking about before to make electricity. You spin a turbine, you're spinning the magnet around a bunch of coils, and it makes electricity. And so the reverse is true too. So there's an interaction between electricity and magnetism. And so in a magnetic field, spinning electrons will align. And they'll either align with the magnetic field, which is energetically favorable. You know, if you take two magnets, they're going to want to align so their poles cancel out. Or they'll align against the magnetic field. And so that might seem weird that they will align against the magnetic field. But if you do that perfectly, if you take two magnets and flip them to where the two north sides are together, and you bring them close to each other, they will repel each other, but they won't rotate around. If you bring them perfectly straight at each other, you'll just start needing more and more force to bring them together. If you let that get out of alignment, then the south pole will be attracted to the north pole is being repelled, and it'll flip around. And so that's the principle of this measurement, is we start off with the sample mostly in this relaxed state. Everything's aligned with the field, everything's good. We add energy and force them to occupy a different quantized state. They go up to this inverted state. And then they naturally, over time, vibrate enough and fall back down. And we measure that relaxation. Anyway. So really, I can't stress enough how powerful NMR is for chemistry. It's like our central instrument. All right. Electron configuration. This is something that you're going to want to practice. You're going to want to just practice doing it. It's a pattern recognition kind of thing. You do it a few times. And all this does is keep track of how many electrons you have in your atom and where they are, what orbitals. Are they going to be in the s orbitals, the p orbitals? Are they in the 2s orbitals or the 3s orbitals? If you fill up an atom, when do you run out of orbitals? So a hydrogen atom only has one s. Lithium only has one s and two s. Carbon has one s, two s, and two p. And so you won't, yeah, this won't be on the screen, but point over here. S block. These have s orbitals. starting at the third group, D block. So here, P block, S, D, P. Hydrogen has s orbitals only. Lithium has s orbitals only. Carbon is in the p block. It has s and p. Potassium has only s. Okay. Iron has s, p, and d. Those orbitals are filled to some extent, at least partially. And then selenium has s, p, and d. I goofed that a little bit, but let me go back one more time. The S and the P's were fine. As soon as I talked about the D's, I realized I was getting a little tongue tied. S orbitals, left side, first two groups. P orbitals, right side, group 5 for the end. Everything in the middle here will have d orbitals. That's true. The thing I skipped was that these atoms here, aluminum, silicon, phosphorus, sulfur, and so on, those also have access to d orbitals. So if you look, that's going to be principal quantum. The quantum number is going to be n is going to be 3. So you expect to have L values of 0, 1, and 2, which is s, p, and d orbitals. Anyway, so as you work through these problems, assigning electron configurations to atoms, keep track of that. Just start noticing the pattern, and after you see it a bunch of times, it will become rote. You won't have to think about it, which is where you want to be. Sort of like doing arithmetic, doing addition. You don't think about addition, you just do it. And so we want to get to that point with electron configurations. All right. And so physically, what does all this mean? When we talk about electron configuration, we're talking about distance of electrons from the nucleus. And we're always thinking about which electrons are more tightly held and which electrons are less tightly held, because that's going to tell us about reactivity. Reactions are electrons moving around from one atom to another. So the less tightly held electrons can go do stuff. The more tightly held electrons can't. I don't really need these slides on the screen. So here is a picture of a hydrogen atom. So you have a hydrogen atom. And then another, we could write the hydrogen atom. So that's how we use our symbolism. Another way that we could picture the hydrogen atom would be this. And another way that we could describe the hydrogen atom would be this. And still another way that we could describe a neutral hydrogen atom would be this. That's all hydrogen. I'm going to put the same information. I'm just going to organize it a little bit better on the screen. I'm going to explain them all. Yep. Yeah. Thanks for asking. And so for the hydrogen atom, we have this, we have this, and we have this. And so this is our symbol that we have for hydrogen from the periodic table. That's all it is. And it tells us actually quite a lot. It tells us it has exactly 1 proton. I don't see any charge on this, so I know it must have exactly 1 electron as well. So here's my picture of 1 proton and 1 electron for hydrogen. I have a mental picture for it. A way that we can describe the electron configuration of hydrogen is to say that this is our N value. So if we're thinking about the electron, sorry, I guess I should say, we want to define the quantum number for this. Quantum numbers. What are the 4 quantum numbers for this? Well, let's figure it out. We know that hydrogen only goes up to the first shell. N is equal to 1. You put the shell here. Then for hydrogen, we know it has to be a 1s orbital. So this is your L. This is your subshell. Principal quantum number, or shell, and then angular momentum quantum number, or subshell. How many electrons do you have in that s orbital? Number of electrons. Another way of visualizing that is to draw an energy axis and say, this is my energy of my 1s orbital, and there is 1 electron in that orbital. That's that little up arrow. The up indicates that it's spin up. So we would say spin up, or plus 1/2. Let's do the same thing for helium. So what do you think goes down here? Try to fill that in for just a minute. And then we'll do lithium, and then we'll move on. And of course, this is a real simple picture that we're drawing, a cartoony picture of our atoms. Let's shoot.
Then when we're writing it out, is L always just defined by like a letter?
Yep. Yeah, L would be defined by a letter in these electron configurations. That's what this is.
Okay.
So if you're
from 0 to n minus 1.
If you're using the quantum number approach, the numbers, then you're right. It should be 0. So if I asked you what is L, you would say in this case it's 0. Yeah. If we're doing electron configuration, you write it this way: 1s1 or 2s1 or whatever. Yeah. Yeah.
Is there only one subshell for every shell? Like, can there only be, it's like, there's, the quantum number was 2 or 3, can it only be like 3s, 3? Like,
No, it will also have everything below it. So if n is equal to 3, then you have access to 3s and 3p, but you also have 2p and 2s and 1s all filled with electrons. Okay.
Is it, like, can you only have 3s or 3p exclusively, or can you have
Both. Both, yeah. So yeah, so far we haven't gotten to a large enough atom yet, but if you get, we'll do that, we'll get to boron, and then we'll have those p orbitals as well in the same shell, right? Yeah. Yeah, good questions. All right. And so yeah, so for helium, we are still in the first period, and so it's still a 1s orbital. This electron is 1 electron. We also have this electron. So if we want the electron configuration for the atom, if we want to know how many electrons do we have in this atom and where are they, then we would just say 1s2. We have 2 electrons in the 1s orbital. If we want to get an energy picture, what's P? I see what you're saying, because I said P over there. It also has S. Yeah, let's forget about that for a minute. We'll come back. We'll come back. Yeah. What I was doing was a very organic chemistry thing, and I realized in hindsight, this is not the time to do that. So it's what I did was it's totally usable and useful, but it probably set us back a little bit because we need to do this first.
You just explain how you got S two.
Sure. Yeah, forget about that whole going up to the periodic table thing. Again, it's a tool, it works. But right now we're trying to walk. So all right. What happened there? I'm so glad I'm signed in. Thank you. Yeah, okay. So here we have, what were you asking about? The
What's not?
why is what?
Why?
Okay, got it. What is the principal quantum number for hydrogen? The principal quantum number N.
Oh,
One. What is the principal quantum number for helium? Also one. So it can only have L is equal to 0, which is s orbitals. So yeah, so I know it's a bit. If n is equal to 1, L can only go up to n minus 1. L is 0. If L is 0, it's an s orbital. If L is 0, it's an s orbital. Yeah. Yeah, no problem. Yep.
So electron configurations, it can be like 1s1, 1s2, and then you move on to the P, right?
I'm gonna get to that. Let's not get confused. Yeah, that's okay. No, you're fine. Yep, everything's good. I just yeah, I want to make sure we build it up in a kind of an orderly fashion. So yep. Other stuff about what we've done so far. All right. So here we have our 1s orbital again. If this red arrow represents the electron here, this would have to be the other electron. They have to have different spins. They have to be paired. You don't normally have to use colors. You just show one up and one down. But that's it. There are 2 electrons here. Each one has its own individual set of quantum numbers. Well, if they're both in the first shell and they're both in an s orbital, L equals 0, and all s orbitals have an ib sub L of equal to 0, then they have to have a different spin. Otherwise, they have all the same numbers. Another way of saying that is if they are in the same orbital, 2 electrons are in the same orbital, they must be spin paired, one up, one down. And another way of saying that has escaped me. Yes. That was the last thing I was going to say. Thank you for reminding me that. Yeah. Yeah. And the last thing is you can only have 2 electrons in one orbital. Yeah. So there are only 2 values of m sub s allowed, plus 1/2 and minus 1/2. So if you tried to add a 3rd electron to an orbital, you'd have to have all the same quantum numbers. There's no way to have a different electron in that orbital and have it have different quantum numbers. That's one way to think about the Pauli exclusion principle, or that you can only have 2 electrons per orbital. But it's probably easiest just to remember that you can only have 2 electrons per orbital. Sometimes we think about these energy diagrams. So this is an electron configuration. Sometimes we think about these energy diagrams, or I think about them as seats on a bus. And every seat on the bus can only hold two people. Now in this weird bus, you have one person's upside down. I don't know why, but that's it. That's the rules. And so, so once you have that, then it's all pretty easy. Every orbital has exactly 2 electrons or less. Well, 0, 1, or 2 electrons. So you can have a completely empty bus. You can have 1 person per seat, or you can have 2 people per seat. And then when we get to building up this diagram, we're going to see that they fill up like a bus. Everybody gets their own seat first, then you start pairing. Okay. Let's go to this one. Let's make it more complicated. Yep. Well, it depends. The red one, the spin is up. The green one, the spin is down.
Oh, so it's not like an overall.
Yes. So yes. So if we're talking about a set of 4 quantum numbers, that defines a single electron. In the case of hydrogen, there was only 1 electron. So we just did it for that. Yeah. In the case of helium, there are 2 electrons. So each electron has to have its own set of quantum numbers. So let's do that. What would the quantum number be for this electron, the red one here? The red one would be n is equal to 1, L is equal to 0, m sub L is equal to 0. And then M sub S is equal to plus 1/2. And I'm glad we did that. And the green one is going to be N is equal to 1, L is equal to 0, M sub L is equal to 0, M sub S is equal to minus 1/2. So there is a difference. Yep. And that's what we'd want to be able to do is figure out, basically, this is why we don't generally go into M sub S, because if we're picturing electrons, you can't really say which electron has plus spin and which one has minus spin. We just know they're paired. Whatever one is, the other is the opposite. That's what we know. And so I wouldn't get hung up on whether it is plus or it is minus, just that if they are in the same orbital, they must be different. That's it. They have to be paired. There are really crazy, well, I call them crazy, question-raising experiments about paired electrons separated over distance, and then the spin of one is perturbed. The other one changes. Distance doesn't seem to matter. And you have information traveling faster than the speed of light in some cases. That's where my understanding breaks down. So, and they call it spooky action at a distance. You know, why do these things remain coupled? Anyway, so that's the weird world we live in. I think it's fun. Moving on. Lithium. Lithium has 2 electrons in its first shell. That first shell must be an s orbital, and it has 2 electrons. That's it for our first shell. Our first shell can only go up to s orbitals. So we start our second shell. Second shell, we start with the s orbitals. How many do we have in the second shell? We have 1 electron, so we only need 1 there. This is the electron configuration for lithium. Electron configuration. All these. If we were to fill this up, we would have 1s, and then we'd also have a 2s orbital. I'm sort of out of colors here. So the 1s orbital will have 2 electrons in it, but there are 3 electrons in my atom, so the next one has to go up to the next shell. We start by filling up all the orbitals at the lowest energy level, then we move up. Then we fill all the degenerate energy levels, then we move up. So I guess my bus has stairs. This bus, ground floor, everybody's going to fill up the ground floor, and then we're going to go to the top, second floor, and then the third floor, except for those people that just wanted to go up there. So anyway. Really?
On the one, I'm sorry.
Please, no.
On the one, where like the 3 and the 4 are kind of wonky.
Yeah.
So you're gonna go to the 4, then go back to the 3, then go to the high
Yep.
3, then
Yep.
like the lower.
Energetically, you're always going to be going up.
Mhm.
It just so happens that the 4 and the 3 cross each other. The 4s and the 3d cross each other on the energy axis.
Why is that?
The spacing between the shells energetically, as you get further and further away, they start to become closer and closer together. Remember, they're occupying a volume. This is the way, again, the way I think about it. Electrons occupy a volume in space. So as you go further and further away, as radius increases, volume increases by the cube of the radius, not by the square of the radius, or not even by linearly with the radius. So what that means is, as you get further and further away from the nucleus, if you want to occupy the same amount of volume, the volume of an electron, whatever that is, you don't need to go out as far, get as much volume again. So if you take a sphere and you double its radius, you have more than doubled its volume. So if you take a sphere and increase its radius by a small amount, you have doubled its volume. So now you have enough room for 2 electrons. If you want to double its volume, if you want to have that same volume added again, you don't need to go out as far again. So you can keep going out smaller and smaller distances. So N isn't changing very much. The shapes are very different in energy. So eventually those differences, that you have 2 different effects, and eventually one's getting bigger while one's getting smaller, and they cross. That's the way I think about it. Yeah, but you don't need to be able to explain it in a hand wavy way like that, but it might help to think about it.
Why is it 2s1 and not 2p1?
The 2p orbitals are higher in energy than the 2s orbitals. We're going to see one with 2p in a minute, and I think it'll make sense at that point. We're going to go up to that. So when we're building up our energy diagram, we start with 1. Then we go to 2s, and the 2p orbitals are higher in energy than the 2s orbitals. Then we go up to 3s, then 3p. And it turns out that the 4s happens to be lower in energy than the 3d. That's that weird crossing point we're just talking about. But for now, we're going to focus on 1s, 2s, 2p, 3s, and 3p. We'll get into what happens after that in the homework, really. We'll see that.
So for the arrows, I'm looking at, if there's one electron, it's always gonna go up, and then if there's 2, it's always gonna go.
That's a way to do it. So long as you always have them paired, it doesn't matter.
Okay.
You can put them all down to start. And then when you start filling in more, you start putting them up. Yeah, but so long as whenever you put 2 in the same orbital, they're paired. And if they're in adjacent orbitals, degenerate orbitals, be in the same direction.
But they always, so they don't always start up.
They can always start up or always start down because it's just an arbitrary assignment. Yeah. Mhm.
And then if there's space for one, never mind, that's.
Okay.
Yeah.
It's okay. Let's do a bigger atom. Let's do a bigger atom. Okay, so we're going to need to. See that. So we're going to skip ahead. We'll skip past boron and go to my friend carbon. At this point, well, I'm just going to put +6 for the nucleus. And then I'll put 2 electrons, so E minus this shell. And if carbon has 6 protons, it must have 6 electrons. We've already used up 2, so it's going to have 4 electrons in its second shell. This is just kind of a shorthand for that picture. 2 electrons in the first shell, 4 electrons in the second shell. Okay. What is the electron configuration? Well, we have 1s orbitals. That's filled. We have a 2s orbital. That's filled. We have 2p orbitals. And we need to put 2 electrons there to use up all 6 electrons. There are 6 electrons in carbon. Carbon is element 6. It has 6 protons. So if it's neutral, it has 6 electrons. Those electrons fill up the orbitals, first 1s, then 2s, then 2p. If we draw an energy diagram, we have 1s, 2s. These are all of my 2p. Remember, when we get into p orbitals, we have degenerate orbitals. As soon as you get into p and d orbitals, you have orbitals of the same energy. S orbitals are all different. P orbitals, yeah, px, py, and pz, and there's no preference for the x direction, the y direction, the z direction. They're all equivalent. So there's same in energy, same shape. The only thing that differs is which direction they're pointing. They're going to be the same energy. And so if we fill this up, 6 electrons, and this energy diagram is going to be the same for all atoms. You can always just draw this diagram and then start filling it up with how many electrons you have. So imagine we took that approach. We didn't have our electron configuration yet. Imagine we did it this way. Carbon, draw an energy diagram for an electron energy diagram for carbon. If that's all the information I gave you, it would say, well, carbon is atom 6, element 6. So this is my energy diagram for all atoms. The start of it, going to have 1, 2, 3, 4, 5. And then this is where we think about the bus. We're going to fill up all the seats before we start pairing. You're not going to just jump in next to a stranger and sit buddy, buddy. You're going to find your own seat. So another way to think about that is orbitals repel each other. Or no, not orbitals. Electrons repel each other. They're negatively charged. So they're going to avoid each other. They're going to go into different orbitals if they can. So we pair in the lowest energy orbital, pair in the next lowest energy orbital. When we get to degenerate orbitals, we keep filling up all the orbitals until they're all filled singly, and then we go back and fill them doubly. Going up one at a time, that's the Aufbau principle. Aufbau, building up. So Aufbau is building up, I believe it is German for something having to do with up. I forget now, but doesn't matter. The point is, Aufbau's principle is building up. The Aufbau principle is building up. Hund's rule, Hund, H-U-N-D, is maximum multiplicity. All your spins, you should fill up all the degenerate orbitals before going back, or you should half fill all the degenerate orbitals before going back and filling them. And so let's see an example of that before we wrap it up for the day. Oxygen will have 8, and that's what we need. 2, 4, 5, 6, 7, 8. We need 8. So 7 would, I think, would have worked, but anyway. So where are we? 8 plus in the nucleus. And we're going to have 2 electrons in the first shell. And I'll never ask you to draw these diagrams that I'm drawing at the very top here. I just wanted them for the sake of discussion. So oxygen, we know just from the periodic table, oxygen has 8 protons. If it's neutral, it must have 8 electrons. If it has 8 electrons and we just start with the energy diagram, we can always say 1s, 2s, 2px, 2py, 2pz, and then we'd go to 3s and 3p. We have 8 electrons, so 8 electrons, 1, there are no other degenerate orbitals, so 2. Third electron, no degenerate orbitals, so 4th electron. 5th electron, there is a degenerate orbital, 6th electron. 7th electron. The 8th electron, the last electron in oxygen, is not going to go to the 3s orbital. It's going to pair in the 2p orbital.
So you don't go to 3.
You don't go to 3 until you fill the 2s. Yep. So stay in your shell until you fill it. And then except for that weird crossing point for D and S. Yeah.
Then it's 2 people.
Yeah, exactly. Yep. So this electron configuration would be 1s2, 2s2, 2p4. Yep. Mm-hmm.
Subshells only have 2.
The actual shells, it does matter how many. There is a maximum number of electrons for each shell, but it varies. Because as you add shells, you start adding different shapes. As you add shapes, you add more orbitals. That's more places for orbitals. And so, yeah, there actually is a fixed number of electrons per shell, but I don't feel like that's worth remembering to me. I always remember the second shell, it has a max of 8. And so that's going to be our octet rule. So that's going to end up being useful. But beyond that, I don't know. It might find it to be useful as you're working problems. I don't think you will. Okay. All right. So that is electron configuration. So that is the Aufbau principle. That is Hund's rule. So we've done 6.4 pretty thoroughly. This first bit. Configurations. Yeah, actually, we've actually got through that. So there we go. Atomic size, ionization energy, and electron affinity. We're going to give this a very fast treatment. Oh, I guess I should say, as you're working for filling electron configurations, you may find this to be helpful. Just for remembering what order they fill in. So if you put all of your all of your S's in one column, so you end up with 1s, 2s, 3s, 4s, and so on. Put all of your P's in the next column, starting 1 down. Put all of your D's in the next column, starting 1 down, and all of your F's in one column, starting at 1 down. Then you go from the top right to the bottom left, and that's the order they fill. It's a visual representation of what we've already seen. So we fill the 1s, then we loop around, fill the 2s, loop around, 2p, then 3s, then we loop around, 3p, then 4s, loop around, 3d, 4p, and so on. That's that switch between the S and the D. Anyway, but that's not what I wanted to emphasize right now. Some periodic tables will show electron configuration on them. That's what this is showing here. So if you want to check your work, figure 6.29 in the book, you can just pick any atom you want and write an electron configuration for it, and then go to the table and make sure you did it right. That's how you can generate a large number of homework problems that way for yourself until you feel very comfortable with electron configuration. I'm not going to emphasize the exceptions, but you should read about them and be comfortable with the idea. You know, that could definitely be like a question on the exam. You know, there's always a little bonus on the exam. So maybe that could be a question that's kind of a little bit, stretching a little bit. But I wouldn't emphasize the exceptions. I would emphasize the rules. Ions will have a slightly different electron configuration. So a cation has one fewer electrons, positive charge. An anion, something with negative charge, has one extra electron. So if you have hydrogen with a positive charge, it has 0 electrons. Hydrogen that's neutral, it has 1 electron. Hydrogen that's negatively charged would have 2 electrons. And so just being able to do that and then just fill in your energy diagram or your electron configuration accordingly. I need to move past this. There we go. Periodic variations. So the 3 periodic variations that we're going to look at are the size of atoms and ions. How big are they? Ionization energies. How hard is it to come up and just knock an electron out of an atom? That's ionization energy. So you run up to an atom and knock an electron out. Then there's electron affinities. How much are they likely to steal an electron from something? That's affinity. How much do they like the electrons that something else already owns? So we're always going to be thinking about going down within a group, up or down within a group, and left or right across a period. We're thinking about when we talk about trends on the periodic table. So for radius, as you go down a group, you're increasing in. What do you think happens to the radius of the atom as you add more and more shells around it? It's bigger, for sure. As you go down within a group, the radius increases. That's what that's saying. So the size of the atom increases. What do we mean by atomic radius? Well, we have those electron clouds around the atoms. If you do the math on it, what you find is this extra weird quirk in the math that those orbitals never really quite go to 0. There's never really sort of an end to how far out they could in principle have electrons. It just becomes incredibly unlikely that the electrons are there. And so how do we define the radius of an atom? We use covalent radii. Covalent radii is saying, okay, we take a molecule of 2 atoms that are the same, and we ask how far apart are the nuclei. And so that gives us an average distance those 2 like to bond. That's what we mean by radius. We know they bond with their outermost electrons. And so the thing we measure to get the radius, or to get the covalent radius, is the distance between the 2 nuclei of atoms. And then we just take half of that and say that's the radius. This idea of effective nuclear charge, as you're reading this chapter and working problems, this is a key concept. For periodic trends, this is a key concept. Effective nuclear charge, the nuclear charge doesn't change for different orbitals. So if you're a hydrogen atom, going back to these pictures, if it's a hydrogen atom, this is a positive 1, period. And so the nuclear charge is +1. Nuclear charge is +2, nuclear charge is +3. This has 1 electron, so those 2 balance out nicely, nice and neutral. There are 2 electrons. They're both the same distance from the nucleus. They're going to get the same amount of positive charge balances out nicely. What about this weird case? Well, in this weird case, we have 2 electrons that are closer to the nucleus on average. We have 1 electron that's further away. That one that's further away is going to be held differently to the nucleus. You could say it's shielded by the electrons between it and the nucleus. So the effective nuclear charge for this electron, for this orbital, is lower than here. the electron and the protons are held less tightly together. This is why molecules react, or atoms react with their valence electrons, their outermost electrons. And I guess that's where we'll pick up next time. So I will see you on Tuesday. Office hours right now, if you are interested.